Thank you, everybody. I'm speaking to you from what remains the United States of America, and we're going to talk today on smart ventilation. We're actually going to talk a little bit around smart ventilation and then sort of zoom in on it, because before we can actually talk about smart ventilation, we have to talk about ventilation and why we do it so that we know what we're doing is smart. So it's always best to begin with sort of a definition, and the definition of ventilation is always important. It comes from the Latin word ventilare, which means to expose to the wind. In medicine, they use the word basically to exchange air in the lungs. To breathe is to ventilate. In buildings, it's not so different. We mean the building breathes to bring air in and out to replace the indoor air with outdoor air. But that is not necessarily exactly the same as indoor air quality, which is the building service that we're actually seeking to provide, or one of the building services we're seeking to provide. Ventilation is a means to that. So we sort of want to look at why do we ventilate, and at least at very broad brush, this level, and I have a list of several things on this slide which shows you the things people have said. Obviously, health and odor are the big things we typically think of is in the building services, but energy is a resultant, moisture is important, durability, safety, sustainability are all part of the building itself, and ventilation can well impact that. So some of these things are IAQ, some of these things are IEQ, that is indoor environmental quality, and some of these are building properties, and they're all mixed together when we talk about ventilation. So I want to spend a little time before talking about smart ventilation to talk about sort of the deep, dark history of ventilation and how people have thought about this over the years. So if we go back to Neolithic times, sort of the species Homo sapien came around about 200,000 years ago, and their key invention was the domestication of fire. And since that time, especially in temperate and cold climates, people have had to deal with fire, and that meant they had to deal with fire inside caves, and that meant they had to learn not to choke themselves to death with fires, which of course they did the hard way. The first homes, as we might think of them as homes, actual structures that were intended to be built for people to be in, were 10 to 12,000 years ago. They didn't actually have closed roofs in the way we think about them, because they all had fires inside of them, or many had fires inside of them. The first chimney that one might recognize was dug up in a village of China outside the city of Xi'an, about 7,000 years old. And they actually had a chimney in that building. Strangely enough, they didn't have doors, but they did have chimneys. So these early people, they knew they had to ventilate fires for safety. They learned the hard way, but they learned it nonetheless. The first civilization in the Mediterranean was 4,000 or 5,000 years ago, and that was the Minoan civilization on the island of Crete. This little diagram is actually a schematic diagram of what perhaps was the largest building in the world at that time, which was the palace, the Minoan palace of King Minos of Crete. And it was a naturally ventilated structure. It was big enough that they actually had to think about how they designed it. And it's built on a sloping site with prevailing wind, and they took full advantage of it, as this drawing tends to indicate. Interestingly enough, there's a bunch of things in that palace that you may have heard as Greek legends when you were growing up. I know I liked those stories a lot. So the thing called the labyrinth, which was the maze people actually got stuck in those ancient stories, is the storage area right here, in this corner. This area here was had very little ventilation, and so they used it as storage. In the lower in this corner down here, I'm not quite sure why these traces are showing up, but sorry about that. In this corner right here is actually where the king's chamber was, because it is the most well-ventilated space in the entire palace. The queen's chamber was right above that, so she could look down the middle atrium and sniff to figure out what was going on. And the other public spaces were up on the top. So that's kind of an interesting thing that early man or early civilizations learned to use. As we go to slightly more modern times, the Romans had figured out how to use combustion safely to both keep away the combustion products and to ventilate and use underfloor heating systems. They were quite the engineers of their time. Traditional societies, however, learned other ways to do it. The American Indians, for example, figured out how to carve chimneys in caves or put combustion outside the living spaces. But early health concerns were more than just combustion as civilization grew. This interesting fact that the first use of writing was done by some of these early civilizations, such as the Egyptians and the Sumerians, and they did not use it to write love letters or derive the nature of the universe. Writing was first used to do accounting. Writing was where you kept track of how many goats you sold to X or how much somebody owed you. And the Egyptians did this, and the middle managers who did it tended to be Egyptian citizens. And in the building of the pyramids, there was quite a lot of writing and keeping track of what was going on. It was an important thing to them. And the middle managers who kept track of how the pyramids were doing noticed something unusual. The stone cutters, which were slaves, but the highest value slaves one had, it turned out to get sick more often if they cut their stones indoors. So after looking at all the data, they decided to move the stone cutting process outdoors, and they got more out of their stone cutters than others. So they learned something about ventilation the hard way. But the first real ventilation standard where somebody thought about ventilation explicitly, the first one I could find was in 1631. Your own King Charles of England decreed that there must be ventilation, that ceilings have to be 10 feet high, that windows have to be taller than they are wide, and this was more a health concern than anything else, but it did improve the buildings, and it improved it quite a lot because 35 years later, as was London's wont, there was a great fire and all the buildings burned down again, and they were all rebuilt under the new standard. And it was quite well appreciated. People thought that the standard of living had gone quite up. It was appreciated so much that in the 18th century, your parliament put in a window tax because people liked their windows so much that that was a way to raise money. The first sick building, in the sense of sick building syndrome, was probably Parliament, because it was probably the biggest building of its era. And the various writers of the day called it foul, rancid, and pestiferous. I was never sure if those were the members inside it or the building itself. I'll leave that for you to decide. But mechanical ventilation was added in 1734 by a design from Sir Christopher Wren. And it was mechanical ventilation because there was something that moved paddles to move air, but what that something was oxen. There obviously weren't electric motors, and there's not much water power and things like that there. But it was deemed to have improved the situation. When Parliament burned down the next century, they decided that that was a good idea, but it wasn't done well enough, so they wanted to really know what the right rate to ventilate was. And they commissioned a study from a fellow named Treadgold, who in 1834 studied it and determined that it was 4 CFM per person, 2 liters a second per person until Brexit is complete. And that was really the first ventilation science. The the scientific revolution is generally credited to Lavoisier in France at the end of the 18th century, but this was the first ventilation science, and it was done by Treadgold, so I want you to remember that date for later. Because now I want to move much closer to current times so that we can talk about what's doing now, because ventilation has changed a lot since then. The last time it really changed in a significant way was the oil shocks of the late 20th century. Between those two times, the industry got a handle on ventilation, and it wasn't really a big issue in the public mind, but the oil shocks sort of changed that, because one had to pay for ventilation with energy, and energy was important. So there was a push for lower ventilation rates, a push for tighter building envelopes after the oil shocks. The International Energy Agency was created as a result of the oil shocks. New products were related, or better living through chemistry, as one of our companies said, so a lot of new sources appeared in homes. So there was a lot of things going on inside buildings that led to unintended consequences to indoor air quality. Shortly, it was about this time that I got involved in this whole field, more first from the energy side. So we ventilate for comfort. We don't just ventilate to keep from dying, as the people in the caves once did. We ventilate for comfort, which is indoor environmental quality. There's two kinds of comfort. Of course, there's thermal comfort, and so sometimes you ventilate for overheating, but I'm not going to talk too much about that. The big kind of comfort we ventilate for is odor control, and that was what the standards of the mid-20th century were all about. How much air did it need to control the typical odors? Occupants themselves are pretty good detectors of odor. We know when something smells, and we know whether we like it or we don't. The biggest odor, though, that we have to deal with is us, people. We emit human bioeffluents. One of the things in that is carbon dioxide, but carbon dioxide itself is not a contaminant of concern at the levels that we talk about things. It's only a surrogate for human bioeffluents. And we learned through data at Kansas State and in Denmark that 2.5 liters a second per person is enough to keep adapted people who've been in the space for a little while, satisfied from human bioeffluents. And these kinds of numbers are going to dominate in high density spaces where there's a lot of people, auditoria, that sort of thing, and probably that much ventilation will take care of everything else too. But if you're in a low density space where there aren't very many people, then these numbers are floors, but we may have other reasons to ventilate as well. And of course, the one that's of most interest these days is health. We're trying to raise the standard of living, and health is very important. Occupants are not good sensors for most contaminants. They don't know when they're being exposed to an unhealthy amount of formaldehyde or PM 2.5 or something like that. So it's very important to know what the key contaminants are, what we can measure harm from them by, and how we mitigate them, and how we use CO2. I'm not going to talk much more about that, but that whole issue of determining contaminants of control, contaminants of concern, is one of the major research activities that we and other people around the world are involved in. What I want to spend the rest of my time is talking about how can we be smart in terms of ventilation with what we know today. So how can we be smart with what we know today? So what does it mean to ventilate smart? And many people have different definitions, and many products claim to be smart because they have their own definition. There is no one. But when I'm talking about it, I want to talk about changing when and at what rate we ventilate to both to reduce energy or provide some other benefit while maintaining or improving the indoor air quality compared to what the dumb ventilation system is. The dumb ventilation system is what minimally meets whatever standards apply at the time, such an airflow every hour of the day. So for energy, we can achieve energy reductions if we're willing to change when we ventilate. because we can operate the system less when there are bigger driving forces, temperature, humidity. We can also take into account exogenous ventilation sources, kitchen fans, clothes dryers, bath fans, things that are happening anyway and that provide ventilation, whole house ventilation incidentally, or whole building ventilation incidentally. If we know how to be smart, we can also take advantage of when homes are not occupied because we know how to catch up when they become occupied. Also, if you have utility pricing signals, because electricity is more dear at certain times of the day, you can optimize for that sort of thing. But fundamentally, we need to maintain the same indoor air quality, which means we need some operational definition of what that means. And from this point of view, we call that equivalency. That is, having the same or better exposure as a continually operating fan for a continually emitted pollutant. That's the definition of equivalency we use with smart ventilation. There's lots of arguments about which pollutants that may not apply to, but we don't even talk about those at all when we talk about the dumb ventilation standards, so I'm not going to talk about that here today. In order to do that, you have to install a fan or a ventilation system that's oversized compared to the steady state, because sometimes you're going to have to ventilate more if you wish to ventilate less at other times. And you do have to worry about peak concentrations that might happen by not ventilating for a long time and then over-ventilating for a long time. Okay, so ASHRAE Standard 62.2 is the first standard to actually include equivalency as an option within the standard. The standard, that version is the 2016 version, which is yet to be adopted, but earlier versions of Standard 62 are adopted in many parts of the US. The current version uses the concept of equivalence and actually has an operational way of dealing with variable ventilation so that you can design around it. So what does equivalence mean in a little more quantitative sense? So it means that if you have a time-varying ventilation rate, it should give the same exposure as the continuous one. And so we have to do a little math to do that, to find out what the equivalence definition is. Now, these rates on this slide are the rates from Standard 62.2. The dumb ventilation rates, that's what's expected to happen every hour of the year, where NBR is the number of bedrooms, and A is the floor area, and you get a number that's for a typical US home might be 0.3, 0.4 air changes per hour, depending, of course, on its size and details. But the principle of equivalence doesn't depend on specifically on what the target rates are, so a different standard could do it differently. You crank through the math and you get an equation for R, which we call relative exposure, the exposure that you would get in that given hour for the actual time-varying ventilation system compared to the dumb one. So R equals 1 means that you're getting the same exposure you would get from the simple dumb ventilation system. When it's greater than 1, it means you have a higher exposure to contaminants, and when it's less than 1, it means you have a lower exposure. Now, ASHRAE 62.2 only says the exposure over the entire year should be the same, so you're obviously allowed times of higher exposure and lower exposure, subject to some peak exposure limits in any 1 hour. You could make it, one could make different limits in different standards. I'm not going to go into the equations anymore, but I do want to give you an example of what we're doing, so that you can get a sense of how this all works. So I'm going to give you 2 examples in what we call RIVEC, which is Residential Integrated Ventilation Controller. This is a specific controller that we invented to do several of the things in smart ventilation. So the examples I'm going to show you assume that you wish to turn off the ventilation system for 4 hours a day. In this case, to avoid peak temperature differences, and I'm going to show you a heating season example. But it could be you could do similar things where you had 4 hours a day of poor outdoor air quality in an urban basin. Could be 4 hours a day when the utilities told you that utility prices were very high. You could move that all around, but that's going to be the example. I'm going to show you some parts where the house is both occupied and unoccupied. We have an oversized fan that's working in, and I'm just going to take you through a complicated looking example. So here's the complicated looking example. This is 2 days, 48 hours along the x-axis of operating on the schedule I just mentioned. You see the purple line going up and down. That is the fan. In this case, this particular example is for a whole house exhaust mechanical ventilation fan. It's oversized by about a factor of 2. And so if you look at where it begins at 0, you see that it's cycling on and off. That's because the controller doesn't need it to be on all the time. It only needs a partial time. So it's cycling on and off to maintain you see the wiggly line just above it, sort of blue-green. That is the relative exposure. That is that R factor that's being calculated, and it's bumping up but not going above 1 as we enter steady state. The red line is what we call the relative dose. So that's a long-term average of the relative exposure. It's in theory, one could extend that to a full year and still meet standard 62 because it says the year average shall be less than 1. Instead, from a practical standpoint, a controller can't look back a year. We have it look back a day, and we allow some excursions, temporary excursions above 1 as long as the average gets below 1. And so that's the red line that you see. So we begin and everything's sort of in equilibrium, and then our 4-hour period of no ventilation starts, and you can see the relative exposure goes up somewhat quickly from 1 to almost 1.8 during those 4 hours. The red line, which is longer-term integration, goes up slower. So, and the purple line is at 0, so because the ventilation system is off. So after the 4 hours, the controller turns on again, and it sees, oh no, we're way too high, so it turns on the fan to full power for what ends up being about 6 hours, and starts pulling those numbers down again. Now, if you look at about hour 11, you see a green square. Now, this is indicative of the fact that this particular day is laundry day, and somebody's running a dryer, a clothes dryer indoors on this particular day, and that's providing extra ventilation. And so that extra ventilation is bringing the system down faster, so the curve drops even lower. And then finally, at about 2 or 3 in the afternoon, the system has recovered. It's gotten back down to its equilibrium level, and by hour 16, it's now back in essentially steady state mode. So nothing else significant has happened for the rest of that day. Now the second day has the same patterns, except that it turns out this is shopping day rather than laundry day, and at hour 32, everybody leaves the house. So the home becomes unoccupied for a few hours, and you can see that the relative exposure stays quite high. We have a cap at 2 on this, so it does cycle a little bit to keep the relative exposure to below 2, and then when people come back home at hour 40, the same sort of thing happens where the fan turns on high and the exposure drops. So this is how a real-time system would work. And sorry for the details, but I wanted to give you a sense of how a ventilation controller would go about its business, saving money, saving energy, and keeping good, acceptable indoor air quality at the same time. But you can see that it's saving 30 to 50% for, these are 4 different heating and cooling systems in different climates that might have been used. And you can save in certain climates that have cooling loads and can use economizers, you can save almost 100% of the ventilation-related energy by having a smart controller. This example is the same pattern as before with one addition which I thought would interest you. Here we have put in a passive stack ventilation system. And so the black dotted line at the bottom shows you how much that ventilation system is operating. And you see the purple line is used a lot less. That is, the mechanical system comes on every now and then because the passive stack system is not oversized, or it's not sized to provide 100%, because if it did, it would provide too much for much of the time. And so this is a way of doing a hybrid mechanical passive system that can cut costs in a variety of ways. So I won't go into the details, but it's the same pattern of occupancy use as the first RIVEC example. We've also been looking at even simpler ways of doing this. So one idea that's getting popular, at least to consider, is if you have a leaky house, something not a high-performance house, but a typical home that has a fair amount of leakage, you know that there's infiltration which happens during the winter and drives a lot of it. Suppose you have a fan that only operates when the temperature outdoors is above a certain amount and assumes that infiltration will take over more or less below that. Well, this is an example of how that kind of system would work. It does not save as much money as the smarter ones I just showed you, but it doesn't require quite the same real-time knowledge of what's happening in the house. And I won't go into the details, but if you look at the black line versus the gray line, it's showing you how much energy you're saving compared to a dumb ventilation system. So let me wind up with some conclusions here. What smart ventilation can do is it can cut the ventilation energy quite substantially compared to a simple mechanical ventilation system. It also gives you the option of optimizing other quantities of concern as we build buildings in an integrated manner, where we look at demand and peak power, we look at comfort issues, we look at exposure to outdoor contaminants, we look at utility pricing systems. You can optimize all these other things and still know that you're providing acceptable indoor air quality. It can also be used in various programmatic needs and retrofit programs and things to help simplify the costs of doing certain things. The biggest thing it can't do right now is be bought off the shelf today. There are no real smart ventilation systems that do what I just described available to be purchased. So what are the smart things for us to do next? And that is, we need a little bit better control systems to know about occupancy, because in my simulation it's easy to say it's unoccupied, but when you want to apply that in real life, you have to have some easy way of doing that. People need to adopt the ASHRAE 62 equivalency options so that they have a way of showing they're complying with codes. It could also be lifted out and put in other kinds of codes. And those codes need to be, we need to have such smart things put into the codes and the rating systems and the utility programs. That's not necessarily an easy thing, because no longer do you just look at the size of a particular component and say, yes, it meets the requirement. It's now got a controller attached to it. And we need to start to commercialize things. There's a couple of manufacturers in the US who are starting to commercialize products that aren't quite smart ventilation, but hopefully soon will be. So looking forward in terms of the science and engineering, in the near term, ventilation has to get smarter. We have to adopt these principles so we can have a win-win situation of improving IAQ and improving all these other factors as well. Taking a step beyond just smart ventilation, we need to get a little bit more quantitative about indoor air quality. I've been very quantitative about ventilation in smart ventilation, but it didn't talk about the contaminants. We are now starting to talk about what are the contaminants of concern, how do we keep them at levels that are appropriate, and how do we trade them off against each other? Because that's something the health guys really don't like to do, but it's a very normal engineering thing to optimize many factors all at once. Longer term, I'd actually like to reduce the importance of ventilation, as we think ventilation and IAQ are the same, but really ventilation is only one small component of IAQ. It just happens to be the one whose knob we can turn. Dilution should be the last choice to provide health. We first need to identify the contaminants and control them before looking to exchange air with the houses. And that brings me to a request I have for you on the line. I have a job for you, which I'd like you to consider. As I mentioned earlier, the beginning of ventilation science was in 1834. Well, we're only 17 years away, roughly, from the bicentennial of that. So that will be 200 years of ventilation science, which I think is enough, actually. So I'm proposing that we have a bicentennial whose major purpose is a eulogy for ventilation rates, because I think they're no longer going to be important by that time. Now, of course, the obvious place to have it is the Palace of Westminster, since that was what started off the beginning of ventilation science, and that would mean the obvious people to host it would be CIBSE, who is, after all, the second oldest ventilation professional society in the world. So I'm leaving this in your fine hands to consider. You have plenty of years to consider it, but I will tell you that the Great Hall is not reserved for that particular day. So with that, I think I can stop and take any questions.
Well, thanks, Max, for checking out the diary of the Great Hall, and thank you also for that excellent presentation. I'll just ask those people who are online, and we got people online from probably around 20 different countries around the world at the moment, which is fantastic. If you have any questions, you can type them into the chat box on your screen, or if you have a microphone and you're wearing headphones, you can ask your own questions. Just raise your hand in the electronic way on the screen, and I'll take your questions as they come. But we can only do that if you've got microphones and a headphones on, otherwise we'll get horrendous feedback through our systems. But I've got a couple, well, in fact, I've got 6 questions already coming in. So we go straight to the questions I've got, and the first ones, and they're coming in quickly now. The first one is Max. ASHRAE presidential member Richard Ruley asks, or says that Fanger used his equivalence of the Olfin decipole to sell the concept of indoor air quality. Do we need to really push this vehicle to sell the concept?
Well, the concept of decipole was a way of quantifying odor, and it was a major brainchild of Ole Fanger, but it never really took off because it required several things. First of all, it required expert panels to rate things, and to my mind, it didn't take off too much because it missed the physical link between the odor of something and what was actually happening. So yes, something that had mold growing in it would smell, but just because you detected a decipole of X didn't necessarily mean you knew what it was. So I don't think decipoles are coming back per se, but that is the kind of quantification one might consider when looking at IAQ more broadly.
Well, that's a shame, but certainly something that perhaps the academic world could take up. Okay, thanks. Thanks for that question. Thanks for your answer. Just a brief question, which I can answer straight away. Question from Ivan, just asking whether we'll be sharing the presentation. Yes, it will be on CIBSEASHRAE.org. Straight after this presentation, and hopefully there'll be a video in a couple of days. So Ivan, you can get hold of that in a couple of days' time. Question here from Glenn Blake Thomas. Now Glenn's a ventilation man, as a lot of us know, and Glenn asks, in offices, how do you see the ventilation rate? I think he's referring to what are the trends in ventilation requirements in offices.
Well, I'm not clear on which way that it's actually going to go. If you look at from the ASHRAE point of view, we're not talking about 62.1. If you break down what's in ASHRAE 62.1 into its people generated part and its buildings generated part, you see the buildings generated part is what I consider quite high because it covers a variety of sins, which are all different in different occupancies. I believe ultimately, as we understand what those sources are and can control them, there is the potential for a long-term decrease in rates, especially as we begin to look at outdoor air issues. If you are building a building in New Delhi, you don't really want high outdoor rates. It's not at all clear that you're better off with higher rates than lower rates because the outdoor air is so awful. And this is true in much of the world, in the big cities of the world. So I think we're going to have to look at rates, and I think ultimately they're going to come down. Near term, I don't have as good a prediction.
Okay, thanks for that, Max. And Glenn follows up by just really confirming, I think, what you've been speaking about today, just saying that although a lot of us design to 10 litres per second per person, doesn't need to be 10 every second and vary in event rate, is sufficient to provide over the day. There's an average to provide indoor air quality, which I think is really what you're talking about there, Max, in terms of domestic.
Yeah, just to add to that, yes, it applies. I mean, I was talking mostly about domestic, but it applies the same in any other thing, but it's not a simple average. That is, applying 100 liters in 1 hour and 0 the next 9 is not the same as applying 10 liters in an hour because of the way it works. So the math is a little more complicated, and the average comes out higher, but you still have the ability to shift things.
Okay, yeah, thank you very much. Question, just to get some further information, I guess, Yasin asks, is the research that you're talking about here, the control algorithms, documented in some Lawrence Berkeley National Laboratory research papers, and can he'd like to use that as a starting point to look at this further?
Yes, we certainly do have papers on various aspects of it. The data I showed you on RIVEC was taken out of publications that we have, and I can supply links to some of those.
That'd be great. I'll add those to the CIBSEASHRAE.org website when we post the presentation. If you can send those to me, Max. Thanks very much.
Sure.
Okay, next, so I'll read as quickly as I go through. I've got a question here actually from Mike. Mike asks, the comparison you made, Max, it was showing some benefits over traditional ventilation methods. Was that over an on-off controller or of a system that ran all day in the building, or was that with a slightly smarter, in its own way, controller which was modulating?
Those comparisons were from what we consider a base system, which is just one which is running at the correct amount 24/7. So there obviously are intermediate ways where you can be a bit smarter about doing it, but we didn't look at those.
Okay, and Nathan asks here, just a clarification. You showed on your chart how the dryer improved the IAQ. Can you just explain that a little bit more? How did it, and how that affected the IAQ?
Well, so at least in the U.S., all dryers are vented to outdoors, and they have a exhaust rate of something like 100 liters a second of while they're running. So essentially, from the home's point of view, this was supplying an extra 100 liters a second of exhaust ventilation, which would added to the exhaust ventilation by the whole house system. So the idea is that if you're doing that, you're capturing any emissions from the dryer itself, venting them directly, as well as increasing the whole home ventilation rate.
Okay, thank you very much for that. Very clear. A question really just perhaps very similar to I guess what I just posed from Mike there, from John Gorsborough, just saying, could you get the same effect, do you think, by using sensors in the house to measure pollutants and PIR detectors for presence and programmers?
Well, the short answer is no. The longer answer is yes. That is what I was saying is the next step of actually measuring the contaminants and making judgments based on those. But to do that, you must be able to measure the contaminants, and you must have metrics that you follow to take those into account. So that's what we call the IAQ metrics project, and that is the next phase of being smart, knowing how many people, whether it's occupied or not, so that you have to supply acceptable indoor quality, what the contaminants of concern are for that particular space, and what their current concentrations are, and what you can do about it. Because you can, of course, ventilate, but if you know that a specific contaminant is high and you have another control mechanism, let's say it's particles and you have filtration available, you could use that instead of ventilation. So that is the next phase. That is where we are going from a research point of view. It's not something one can act in a real building on quite yet.
Okay, thank you very much. Got a question here, and this is from Chang Zhang, and he's at the Technical University of Denmark, and of course they're well known for their work in comfort, of course. Well, first of all, he comments, great presentation. And he says, well, here's a provocative question for you. How about just training people to become smart and automatically open and close windows rather than use complicated systems and having to maintain them?
Well, I'll answer that in a couple of ways. One is people are not very good indicators, as I said, for health purposes, so they won't know when they should open their windows from health purposes. Second of all, I am not a believer in training people to make their buildings work right. I'm a much bigger believer in buildings that work right for people. So that, yes, it is certainly possible to do everything yourself without any systems, but I don't believe the vast majority of people are ever going to do that or want to do that. We, who are experts who think about these things and care, might be on guard at all times to do this, but I don't actually think it's a very good solution for a broad-scale solution.
Okay, now to be fair on Chang Zhang, he did put a rider on that question, which indicates that he's considering developing such sensors so that it can be controlled. The pollutants can be controlled that the human being can't sense. Okay, moving on to our next question. I've got a question here from Rowan, and it was actually looking at one of your specific slides or a comment you made, Max. You suggested that maybe in just a passing remark, but it could save 100% of energy. Wasn't quite clear how it could save 100% of energy.
Okay, this is a situation which is probably not British, but in much of the southwest of the U.S., the energy is dominated by in milder climates where during much of the day the outdoor air is at acceptable conditions. So we have things called economizers, which basically ventilate at very high rates, perhaps 30 or 50 air changes per hour. Their purpose is not ventilation, but to keep from overheating. so that when the air is pleasant outside, but if you boxed up your highly efficient home, it would overheat, you can run these economizers for many hours of the year. For about 6 months of the year, my economizer at home will run 9 to 12 hours a day. If you have such a situation and you are taking ventilation credit for all of that extra air, you can not ventilate for perhaps 12 hours because you ventilated so much the other 12 hours. In such a case, you've basically gotten rid of the entire ventilation energy load because you don't ever need to ventilate for IAQ because these other things are happening. So that's an extreme example, and that's why that was as much as, I think 30% is a much more realistic sort of number, but it can get up that high.
Okay, yes, we do use economizers in our ventilation systems here in the UK. Well, I note we're about 10 to the hour, and I want to make sure we include sufficient time for the guys at CIBSE in London to input their ideas. So I'm going to hold on the questions just for a few minutes, and I'll pass back to Tim Rook, who's at the CIBSE headquarters in West London. Over to you, Tim.
Thank you. I think I'll hand straight over.
Oh, hello. My name's Peter Diamond. I come from an air filtration background. I don't know if Max can hear me, but I'm very interested in the overall picture that's been put across, but I don't feel there's very much focus on background airborne contaminants. We have a very real problem here in cities in the UK certainly, and I imagine across most of Europe and the rest of the world, with traffic emissions comprising mainly of fine combustion particulates, PM1, PM2.5, PM10 as a range, and also nitrogen dioxide, both of which have been labelled as Group 1 carcinogens by the World Health Organization. We have metrics from the World Health Organization for these problem outdoor source contaminants, and we also have effective means by filtration of stopping them coming into buildings in cities, and I just wondered what your feelings would be about drawing attention to this sort of solution.
Well, the answer is we very much agree that these are big problems. That wasn't the focus of today's talk, but the contaminants of concern that we talk about, PM2.5 is number one on that list of contaminants by far, and filtration, which is fortunate in one sense, it's the contaminant that we can most easily control through filtration. Outdoor air contaminants, as I mentioned briefly, are very real in most of the cities of the world. They're not all as bad as Beijing and Delhi, but even in Western cities, outdoor sources are quite significant. Most indoor ventilation standards blithely assume that outdoor air is okay because they're trying to make standards for the building design, not for the specific location, but the IAQ metrics that I briefly talked about would very much take these things into account. So we are quite concerned about these. That's part of, we're not ready to be smart about it yet. You can't get cheap, reliable particle sensors to put in all over buildings, and domestic buildings having filters that have to be maintained has its own set of problems. So there's all sorts of issues, but I very much agree that it's a high priority area.
Certainly, we've had a lot of concern, particularly in schools. In the City of London, for example, there are about 1,000 schools within 150 metres of arterial roads, and there has been a lot of concern voiced about air quality in schools and indeed hospitals, where you have to put in supply air from outside, and of course it draws in these contaminants adding to people's problems, and health is an issue, and indeed working performance. I mean, we need school children to be receptive to new ideas and to be able to take on new levels of learning as required by our new technological society, and so we need to get things right for them and for the future.
Absolutely. There's a tough balancing act to balance indoor generated pollutants with outdoor pollutants. One of my biggest concerns, there seems to be a European-wide interest in natural ventilation, meaning operable windows, and of course if you do that you have virtually no ability to filter the outdoor air when it's not acceptable. So what might work well in the countryside will not work at all well in the city. So these are very real problems, and all I can say is that yes, you have to take them into account.
Thank you very much.
Okay, thanks very much, Beezer. Anything else from London that you wanted to raise? Otherwise I'll go back to the last couple of questions we got.
Yeah, we've got another question here, Tim.
Okay, carry on.
Yeah, my name is Giuseppe Borghese. My interest is in air quality again. I'd just like to, because obviously the smart ventilation is, at the moment, the way it's configured is primarily aimed at energy saving. But obviously the contaminant issue is obviously something you're working on. How much of an effect is that going to have on the benefits of energy saving? Because normally one conflicts with the other, because you're trying to ventilate and dilute to reduce contaminants, but that has an effect on using more energy. How much of an effect is that going to have on the benefits of smart ventilation?
Well, clearly you're right. When the only option you have to get rid of an indoor contaminant is to increase ventilation, then there's a very direct conflict. Now, the smart ventilation, as I have described it, is one way where you can save energy and still get the same IAQ, or get better IAQ for the same energy by ventilating better. You know, when it's cheaper to ventilate more, and you can do better. When we move over to talking about contaminants, how much ventilation you might need will depend on how big the sources are, and do you have any other source control mechanisms. It could conceivably save quite a bit of energy if you handle the sources correctly, but if you handle sources poorly, it could wind up costing energy to provide the same level of indoor air quality. Our bottom line is we think minimal indoor air quality is set by whatever standard applies, in our case ASHRAE 62, and we want to provide that service at the cheapest possible price. But you could also go the other way and say, well, could I provide better IAQ at a moderate price? Those are all things that one can do, but IAQ is the fundamental thing that we start with, and then we just try to provide it as efficiently as possible.
Thank you.
Okay, is there anything else from Beezer?
Have you got more questions online, Tim?
Yep, we have some more questions here, and a couple of statements which I can make, and we've only got a few minutes left, so maybe if I pick these up, and then we'll finish off by passing back to Beezer when I've covered these, and then you can use that opportunity to make any further statements or questions, if that's okay.
That's great, thank you.
Okay, well, as I say, we've had some more questions come in, some statements come in. Let's have a look at those. Several of them are really saying, and you know, we're heading towards smart IAQ meters and wireless integration. So we may well be able to see this next stage that Max is speaking about rather earlier than we might expect. And for those people who work in the UK, of course, there's an excellent reference, particularly if you're working in school accommodation, that's been brought to my notice by Nathan Wood, BV101. If you just Google it, you'll be able to find BV101. It's just under revision at the moment. You can see the draft version on there. That's the ventilation standard for schools, but that's got a lot of very good information in there on air quality. But interestingly, Max, I don't know if you've referred to that document at all, but the new edition that's just rolling out at the moment, it's been under consultation, will also include much more information on indoor air quality as well as outdoor air quality and the effect it has on the indoor environment. So that's a great reference. I've got a question here based. I think you probably answered it, Max, in what you've said. Just to check, the system that you've spoken about today, is it being purely modelled in a modelling environment, or has it been physically tested?
Okay, before I answer that, I want to give another plug that the Air Infiltration Ventilation Center has just come out recently with its Technical Note 68, which is on residential ventilation and health. It covers many of the issues that we've talked about today, so people may want to get that. Look at AIVC.org, and you can find that. The UK is a member of the AIVC, so has access to it. To answer your question, the particular data that I showed you was simulation data. However, we have built and tested these devices in the field. But of course, they're not commercial. They're laboratory wired up and type devices. But we have measured them in the field. It's always much tougher to get a sense of the savings from doing that in the field, because real life never gives you 2 exact years or weeks of the same thing to compare. But we do have field data from these various experimental options that I showed you.